Hello everybody, let us start today's discussion. We have come to Unit 3 now. We will be discussing uh, rigid bodies in this unit. And to start with, we'll, we'll talk about the kinematics of the rigid bodies. Because as we have discussed in one of the initial classes, so that is where we should start. First kinematics, then mechanics, then dynamics. So let us start with the kinematics of the rigid bodies. So how do I describe the motion of a rigid body? Before going there, let us ask the question, does rigid body exist in nature? So to answer that question, you have to go back to the question, what is a rigid body? Well, we will say that rigid body is a collection of particles when the distance between any two particles remains the same. Right? Now, if the distance between any two particles remains the same, we may be tempted to write it this way. So that gives us constraints, right? So these are this gives us some constraints on the distribution, on the configuration of the particles. So let's say that we have n particles, and you agree that n particle has 3n coordinates, and this constraints how many of them will be there. Well, every pair, the distance between them will be fixed, so I will have nc2 such constraints. So apparently the degrees of freedom of such a rigid body will be this, and if you calculate that, you will see that there is a question mark now, because above a certain value of n, this will give you negative degrees of freedom. So this is not quite correct. Why is it not correct? It is not correct because all these constraints are not independent. Sorry. Okay, so that you have to be careful that this is not the formula to get the number of degrees of freedom, because the constraints that you are talking about, there can be, so you can derive one of the constraints from the others, so then this will not be true anymore. One example is very clear. So there are these 4 bits arranged in a square, and we say that the distance between any of these 2 bits are fixed. But you see, if I fix this distance, and this distance, this 3, and then I fix Okay, I also fix this one and I fix this one. Now there is no way these bits can move around anymore. So let me just highlight them a little bit because everything has become a dot. So the other diagonal, though, that will be counted in your NC2 is not required to fix the uh, degree of freedom of the system. So that's a non-independent constant. That constraint that the distance between these two particles are fixed can already be derived from the other four that we have used up. Okay, so one has to be careful. So that is why I asked you to try to figure out at least three different ways why the degrees of freedom of a rigid body is 6. And this is one problem that everyone has, that you first derive this expression to get the degrees of freedom of a rigid body, and then you soon realize that for large n or n greater than a certain value will not need to be large, this formula cannot work. Nevertheless, we talk about the concept of rigid body, and this is what is a rigid body. But does such body really exist? Is it possible that the distance between the bodies are always fixed? Is that possible? So let us ask that question. If we see that such bodies actually doesn't exist, then obviously there is no point of studying unit 3. And if we see that more interestingly, if it's an approximation and only valid for certain cases, then we have to be careful. Then I should not use rigid body dynamics for certain cases. Okay, so let's have a rod and ask the question, can I call a rod as a rigid body? So what do you expect? So all time, whatever I do to this rod, which coordinate system I go, whatever I do, all the particles between the rod will remain fixed. The distance between them will remain fixed, right? That is what I mean by a rigid body. That's the definition. Imagine now I hit the rod from the left hand side by a force F. Use a hammer to hit the rod from the right hand side. Sorry. What do you expect for the rigid body? As soon as this point start to move, say it was at rest initially, this point will also start to move at exactly at the same time. Because it's a rigid body, if this point has moved and come here, this point has to move and move by the same amount, otherwise it will not remain as a rigid body. But is it possible? If that is possible, then this point in the rigid body, which I call say L, and the point in the rigid body R, they're communicating an information amongst them in infinite speed. As soon as I hit R, L knows that R being hit and it has to start to move. They may be like, if you wish, they may be 1 light year apart. They're quite far away. So light will even take 1 year to go from R to L. But if there is a rigid body so big, if I hit R, L, which is 1 light year apart, will start to move immediately. Definitely that is not possible. So if I consider relativity, then rigid body does not exist. You should be happy because then you don't need to study unit 3. But there is a catch, but that rigid bodies are very good approximation for motions with velocities less than c. much less than the speed of light. So then you have to study unit 3, because now most of the motions that we see around us are motions which are having velocities much less than speed of light. For all of them, the rigid body approximation will work out. But remember that when you are talking about relativistic moving objects, then you cannot use the rigid body approximation. And it's a very important message which I wanted to give you. Okay, so with that much introduction to rigid bodies, let us move around and let us just ask the following question: how to describe the motion of a rigid body? So yeah, assuming that the rigid bodies exist, so then how do I describe the motion of such a body? Well, so when you try to describe the motion of any body or any system, what do? We may start with our 3n coordinates. Imagine there is a rigid body, which is imagine that you have a chalk. I could have shown you a chalk if you are actually present in a class. How many particles do you have in here? Uh, Sometimes Avogadro number, so maybe say 10 to the 26 particles. So that now that is my n. So I have around 10 to the 26, the order of number of coordinates. If I write in Cartesian components, it's 10 to the 26, around 10 to the 26. Well, you cannot even start with by writing the Cartesian components of this and then start to use the constraints to reduce it to the number of degrees of freedom. In this case, you have to start with the number of degrees of freedom only. You have to start with the approximation and the concept of the rigid body. So how many generalized coordinates do we need to fix the motion of this body? How many generalized coordinates? So allow me to write this as GC, need to describe rather the motion of this body. This was one of your exercise, and most of you have got it right, and some of you had confusion, but the number is 6. And very simply, we can say why it is 6 is one of the ways of envisioning it is that I take a origin and I fix any point in the rigid body, any point, not necessarily be the center of mass, any point. And that point has to be described by 3 coordinates in space. So I need 3 coordinates. If this point is the center of mass of the body, then that describes the motion of this body. If you see the body from very, very far away, where you cannot see the dimension of the chalk, so you will not be able to figure out that it is rotating or not. So all the motions that we'll see of that chalk, if this points towards the center of mass, is translational motions. And now, if I go to the center of mass and look at any other points, they can only rotate around the center of mass. And because you are living in 3 dimensions, there can be rotation about x, y, and z axis. So I will have 3 rotations. 3 translations and 3 rotations combined gives you the 6 coordinates, 6 degrees of freedom. Right? So this can be arrived at by many different ways. This is one of the ways of arriving at it. Okay. Okay. So now let us ask the question that how do I describe the motion of such a rigid body? So I know that I need six generalized coordinates, but what are these six generalized coordinates? So the rest of the discussion today will be to figure out how will I describe the six generalized coordinates or the change of the six generalized coordinates as time progresses. Okay. Now let me tell you before we go any further that the entire discussion on rigid body will be from Classical Mechanics by Goldstein. Okay. The entire discussion will be on this, and I request you to revise matrix mechanics. Not matrix mechanics. Whatever you have learned about matrix so far in your mathematics courses, or if you had a physics, mathematical physics course, that course, revise about matrix. Okay. Because that will be using a lot in these discussions. Fine. So with that much, let us start formally to describe the motion of a rigid body. So what we do is we start by drawing these three axes, which are the three axes not at the rigid body, but at some observer who is seeing the rigid body from outside. Okay, so I have x, y, and z. So this is fixed at a point in space. Okay, so this system x, y, z, because the origin of this system is fixed at a point in space, we call it space set of axes. Okay, now what I do is I have the rigid body here. Okay, so I draw a radius vector which goes to the center of mass of the rigid body. Fine. And then usually uh, depending on the symmetry of the body, but what I have drawn here is completely asymmetric, but there is some arbitrary choice of three axis system here. Okay, they are orthogonal again, so they are 90 degrees to each other. It may be my bad drawing which is showing them a little different, but these are three axes which is attached to the rigid body. What do I mean by that? If there is a point when I am drawing this imaginary line along y, if there is a point here, as the rigid body rotates, the axis always goes through that point. Okay, so this is attached to the rigid body. So if I give you a more concrete example, so if this is my rigid body, there is one axis this way, there is one axis this way, and there is one axis this way. So when the orientation of the body changes, it looks like this. And let me level this axis x, y, and z. When the orientation of the body is this, so this is still the y-axis, this is still the x-axis, and this is still the z-axis. Okay, and these axes we have called the primed axis. So just to distinguish them from the space set of axes, we call this prime axis. So these are attached to the body, so we call this body set of axes. Why do we choose these two different sets of axes? Well, it is clear now. Any translational motion we can specify in terms of the space set of axes, because you see that tells us how the center of mass moves. So which means now I can specify any translation with respect to that, because translation is of the center of mass. And any rotational motions we can specify in terms of the space set of axes. Okay. Now, obviously, if I have these two sets of axes, it makes things more complicated. I should be able to write down one set of axes with respect to the other. If I can do that, so as you see that in the generalized coordinates, we do not use different origin coordinate systems. See here I have two coordinate systems with its two origins and all. So I want to write down. So how do I describe orientation of x prime, y prime and z prime in terms of XYZ orientations. Why? Because that is what I will tell us about the rotations. So this will tell us about the rotations. Right? As we said that as the rigid body changes its rotational orientation, the direction of this axis changes because the axes are fixed with the body itself. So how do I specify? So now what I have to do actually, so you see I can define unit vectors here. So I cap along this, j cap along this, k cap along this. Similarly, I prime cap along this, j prime cap along y prime, and k prime cap along z prime. Right? I can do that. And then I ask the question, what is I prime cap in terms of I cap? Okay, so let us just draw a simple cartoon here and a simple coordinate system here again and ask that question, how do I figure that out? And now I prime cap is a direction. Say that direction is this. It may look different in the previous plot, but say this is my direction in this particular, in one of the orientation, the x-axis of the prime coordinate is directed this way. Okay, so one way of writing this, the direction of I prime in terms of the xy and z coordinate, the components of it along the xy and z coordinate, is to take the direction cosines of this. So which is nothing but the cosine of this angle, the cosine of this angle, and the cosine of this angle. Okay. So how do I do that? Well, it's simple. I know that if I take this, so if I call this angle as theta I, I prime, because it's the angle between I and I cap and I prime cap. So this is nothing but cos theta I prime. And instead of writing all these complicated names, just let us give that a name called alpha 1. And similarly, as you see that if I get I prime with j, let me just be consistent. If I get I prime with j, I call that beta 1, alpha 2. And if I have I prime with k, I call that alpha 3. Okay. So these are the three components of the unit vector I prime along x, y, and z. So obviously I can write now the unit vector I prime. The component along x is this, and the unit vector along x is this, plus alpha 2 component along y, and the unit vector along y, plus alpha 3 component along z, the unit vector along z. And you will agree, so this is for the vector I prime, which is the direction of the x prime coordinate. So similarly, I can write for the y prime coordinate, I can define, say, j cap prime. So, and then let's call this beta. So this is beta I cap. And you know now what is beta 1. So beta 1 is, j prime cap dot I cap. Okay, that direction cosine. So let's call this gamma. It's essentially letting me write down the prime coordinate systems, which is the body set of axes, in terms of the space set of axes, the unprimed coordinate system. Actually, I can do the reverse also. If you notice, if I can also write I in terms of I prime, j prime, and k prime. How will I do that? Well, again, it's simple. So if I want the component with respect to I prime, what all I do is I multiply by the direction cosine this. If I want the component with respect to j prime, I multiply by the direction cosine this. And this is, if you think, it is very simple that you know. So this is the projection of the vector I along that particular coordinate or direction. Okay, so just to complete this, and what will that be? So this is alpha 1. What is ij? So that will be rather now beta 1, and this will be gamma 1. So I may be able to write down this now in terms of coordinate transformations. So let's see what happens if I have, say, I have a vector r. So this is any vector r. So any radius vector r. So let me write radius vector. We'll come to any vector shortly. So how do I write this? So this is x, y, z. See, so far we are looking at only the unit vectors, but this is any vector r. Now this will have three components, right? So it will have a component x, component y. So what is the component x? It is r dot I cap, right? So projection of r along the x-axis is the component x. Similarly, projection of r along the y-axis is component y, and projection of r along the z-axis is component z. But you see, I can also take the projections along the I prime axis, and that will call x prime. Similarly, right? So it should be k, and here also I should mention that this is k, right? Now this x prime, this x prime, which I write r dot I prime, can be also written, first I write r in terms of the xyz component. So this is xi cap plus yj cap plus zk cap, and then dot I prime, and then you immediately see that this is nothing but x prime in terms of, I can now write xyz, x into I dot I prime, which is alpha 1, plus y into j dot I prime, which is alpha 2, and z alpha 3. Similarly, I can write for y prime and z prime, and consolidatedly I can now write in a matrix form. This is why I asked you to revise matrix, and you will see a lot of things about the matrix will come. The rotation is represented by matrix most efficiently. So if I have x prime, y prime, z prime, these are related to x, y, z in the following way. And the inverse transformation also exists that we have seen. You could have written down x, y, z in terms of x prime, y prime, z prime with the inverse of this matrix. Now, if it holds for a vector r, so this I can write, okay, so let me write a shorthand for this. This I can write now the vector x prime equals, this is a transformation matrix T times vector x, right? If I have any vector, so this, remember that these, let me change the notation a little bit. So let me write this as r, because that's what we have used already, and that is what usually we use for radius vector also. So this is the shorthand notation. The T is the entire matrix. Now, if you consider instead of a radius vector, so we were, let me draw it again. So you are looking at how that radius vector will change in a coordinate transformation. But I can have any other vector, any arbitrary vector like this, say A, but this can be written in terms of two radius vectors always. If this is R2, right? This is A. So now, if I want to figure out that how will A look like in terms of its components in the primed coordinate system. See, here we have written the radius vector in terms of the unprimed coordinate system, and this is the same radius vector written in terms of its components in the primed coordinate system. Similarly, so unprimed is the body set of axes, primed is the space set of axes. Similarly, here what I am doing is I am asking, okay, so this is the vector in terms of R2 minus R1 in the body set, in the space coordinate system. What will be the vector in the body coordinate system, or the components of the vector in the body coordinate system? And that is simple. That so this, how will I do this transformation? So what we do is we transform R2 and we transform R1. This is metric operation, so they are linear operations. This I get R2 prime minus R1 prime, and that is what is A prime, right? So which means A prime, which is any vector, also transforms by this particular transformation matrix, this transformation matrix. Nice. Now I have these 9 direction cosines, alpha 1, alpha 2, alpha 3 to gamma 1, gamma 2, gamma 3. What are these telling us? These are telling us how this three space set of body set of axes are oriented with respect to the space set of axes. Well, that is the rotation that we are talking about, right? So this 3 alphas, 3 betas and 3 gammas, total 9 of these components must be then telling us about the rotation of the rotational orientation of the body. So rotational orientation, right? How many of them are there? 9. But that is not good, because see, you see that we said that there must be only 3 coordinates which are specifying the rotational orientations, but now I ended up having 9. That is not good. Which means that all of these, all of the alphas, betas and gammas are not independent. There must be 6 constraints, there must be 6 constraints or conditions in them. Okay, before I go any further, let me go back and tell you one thing which is very important here, if you have not already realized. See, we are talking about, we are interested in here. We know that how to talk about the translation in terms of the generalized coordinates is just these 3 axes, three components of any vector, any radius vector to that center of mass. But we really have not dealt with rotation before. So we are trying to describe rotation, and we realized that describing rotation is nothing but describing a transformation from the space coordinate systems to the body coordinate system. And that transformation can be written in a matrix form, so it's a 3 by 3 matrix only. And that has 9 parameters. So these 9 parameters should have all information about the rotation of the system. But then we realized that the rotations should be described only by 3 parameters, but we have 6 extra. So there must be 6 conditions on these 9 parameters. They're not independent to each other. And if I use those 6 conditions, then it will reduce from 9 to 3. 9 minus 6 is always 3. So what are those 6 conditions? So let us try to figure it out. Now remember that our I cap prime, say, is given by alpha 1 I cap plus alpha 2 j cap plus alpha 3 k cap. And similarly, I is given as alpha 1 I prime plus beta 1 j prime plus gamma 1 k prime. Now we have conditions on these unit vectors. So what are the conditions of the unit vectors? So first condition is that they are unit. So if I do this, that must be 1. Similarly, and the second condition is that if I take dot product of any two different unit vectors, obviously from the same group, prime group or unprime group, they are always 0. Okay, so let us calculate what is I prime dot I prime. Well, this is supposed to be 1, that is what I said here. So if you calculate this, what will I get? I will get alpha 1 I, so I am using this expression, and then dot alpha 1 I plus alpha 2 j dot with alpha 2 j plus alpha 3 k dot with alpha 3 k, and then I will have cross terms. What are the cross terms? The cross terms are the cases where I have I dot j, I cap dot j cap, but those are all 0. So the cross terms are all 0. And for the remaining terms, I have this I dot I, which is 1. So this essentially becomes alpha 1 square plus alpha 2 square plus alpha 3 square. And what is that equals to? That's equals to 1. It's coming from there. Okay. So I have these conditions. So this is obviously not only true on alpha, but also true on beta and gamma. So I get 3 conditions there. Similarly, just you can try to use this, which is equals to 0. So this will give you 3 additional conditions. Now all these I can summarize in the following way. So this is homework. Figure out what are these conditions. Just use the exact same way. Proceed the exact same way that we did before. This is delta Ij. Okay. So alpha. So if I have alpha 1, I is 1, j is 2. So I'll have a condition alpha 1, alpha 2, beta 1, beta 2, gamma 1, gamma 2. But if I and j are different, so this is a Kronecker delta, which means if I equals to j, this is 1. If I not equals to j, this is 0. Okay. So if I equals to j, that gives you alpha 1 square plus beta 1 square plus gamma 1 square equals 1, etc. So now you realize that, so how many, so before we leave this, so let us ask the question, how many of these conditions are here? Well, there are 6 conditions. Why there are 6 conditions? Because you see, in any of this, if I interchange I and j, then obviously beta I beta j is same as beta j beta I, so which essentially means that I can have 3 conditions when I is not equals to j and 3 conditions when I equals to j. So this corresponds to these and the ones that we'll get from here. Okay, so I get 6 conditions, 6 constraints, and these are coming from the fact that the orthogonality of the orthonormality of the eigen the unit vectors. So the unit vectors norm or the magnitude is 1 and 2 unit vectors are orthogonal to each other. These two combined is called a property called orthonormality. Okay, so now we realize that we are having a type of transformation which is very special. The transformation matrix is now given by this alpha 1 . But that is not enough. With conditions that alpha I alpha j plus beta I beta j plus gamma I gamma j is delta ij. Okay. So this type of transformations are called orthogonal transformations. And this matrix is called an orthogonal matrix. Okay, so please read the properties of the orthogonal transformation. So this is there in Goldstein in detail. I hope that you have already done it in your matrix class. So because of that, I don't want to repeat it here. For this purpose, you can just have, so there is a section on this in Goldstein. You can just have a look at that and read. If you have any problem, obviously, we will discuss in the discussion sessions. Okay. So we realized two things here. One is that the rotations can be given in terms of this orthogonal transformation, which means that if I now think of, so let's take an example. So this is my space coordinate system. Region is fixed in some space, and say the body coordinate system is here, x prime, y prime, z prime, o prime, body coordinate system. Initially their axes are aligned. As the time goes, what happened is that these axes are rotated, and that is the rotation that we are talking about. So this is at t equals to 0, this is as t equals to t. Now you realize that this motion of rotation now can be thought of as a coordinate, as a transformation of this shot. Okay, so if I have to go from or see how the orientation of this body changes because of rotation, that can be completely done by a transformation matrix. But then that transformation matrix has 9 parameters, and we realize that only there are 3 independent parameters. So obviously this direction cosines are not good choice of the generalized coordinates. We need only 3 of them, we have 9. We do have some conditions between them. So these conditions are like just like the constraints, but we need to figure out something better than the direction cosines to describe this rotation. Okay. So that is what we are trying to, we will now try to do, that what can be thought of as the direction cosines. Okay. Now, these are orthogonal transformations, as we have already said. The orthogonal transformation, now this is represented by a matrix, right? Let me tell you a little bit about the matrix here, because that part will be required for us right now. So orthogonal transformations, a 3 cross 3 matrix. Right? Now I can think of the following case. Just like we said that as time goes from t equals to 0 to t equals to say t1, it comes here, it may go to some other orientation at t equals to t2, right? So the passage of time, and as the change of the orientation of the system as the time goes on, is represented by a series of transformations. So I can now, so at t equals to 0, so to t equals to t1, to t equals to t2, we can think of this, say there is a transformation which is t to 1 from 0, there is a transformation from t to 2 from 1. Okay, do two different transformation matrices. One takes from this configuration to that, the other takes from this configuration to that. Now it turns out that in general, it is not true that this, in general it is not true. Which means that if I do this transformation first and then do this transformation, the system may not come to the same orientation. Okay, and that's important. So let me tell you why one may expect that it will come to the same orientation. Imagine a translational motion in one dimension. So say at t equals to 0, the object is here. You do a transformation. So this is my axis. So let me level them, otherwise you will not be able to figure out where is the system going when. This is t equals to 0. Let us come to t equals to t1. Now what has happened is 0, 1, 2, 3, 4. What has happened is there is a translation. The particle has come here from there. Okay, so this is from there to there. The translation vector is this. This will give me the transformation. So what all I have to do is here, if it is r at t equals to 0, r at, if this vector is, I call translation, okay, r at t equals to 1, that will be given by r at t equals to 0 plus this vector, right? That vector is giving the, is essentially this vector from 0 to 2. And now I think of another translation. This time the object has come here at t equals to 2, and the translation is only this much, right? So that is t to 1. So I say that r at t equals to 2 is r at t equals to 1, t1 plus t translation to 1. Now this I can write as, this is just that. So this I can write as r at t equals to 0 plus right, and it is the because I can arrange the positive, they're just added up. I can first add the second translation and then add the first translation, and I will end up at the same t equals to 0 spot, right? Which means that first I go by one step. So let me use a different color here. So first I go by one step, and then I go by two step. Then I will end up at the same place, right? So this type of things is called commutative, that it doesn't matter which way you do the operation. But it turns out for the case of the orthogonal transformations, the rotations, it is not commutative. It does matter how you do the transformations. Okay, that is one point. The other point is, now how do I mathematically write the combine these transformations? So let's see, how do I mathematically combine these transformations? So say I have a vector A, as we are talking about earlier, and it is being so it is being rotated once, so that is the orthogonal transformation matrix, which gives me the vector A prime. Okay, and now I have the vector A prime, which is rotated another time, which gives me the vector A double prime. But A double prime now I can write as T2, and A prime is T1 times A, right? Which means if I want to go from A to A double prime, so I have this entire matrix, which if you wish I can write T21, which is this. So two corresponding rotations essentially means just multiplying the corresponding individual rotation matrix or transformation matrix, and that will give me the total rotation given by these two corresponding rotations, and that multiplication is the matrix multiplication, right? So now I have this orthogonal transformation matrix, I just write T matrix plus matrix multiplication. These two forms a group which I called the orthogonal group. And I assume that you have studied group already, and either in mathematics or in mathematical physics, because it's a concept that you learn even nowadays. It's a concept that you learn in 6th standard, but maybe you have learned it very recently, but you know what is a group. So this group is called an orthogonal group and is written as O, and with n, where n is the dimensionality of the group. In this case it is 3. The dimensionality is 3. Okay, so let us, so this is O3. These are giving rise to the rotations. So entire matrix operations in the group operations now are going to be very useful. Now there is a catch here. When you talk about orthogonal group, the orthogonal group or all the members in the orthogonal group actually does not represent rotation. And let me give you an example. Let us consider matrix. So all the matrix that you can think of, which is a part of the orthogonal group, should then represent rotations, but that is actually not correct. So let us think of one example, which is the diagonal elements of my all minus 1 and 0 otherwise. So determinant of, so if I call this S, determinant of S is minus 1, right? The question is that whether such a matrix corresponds to any rotation. Okay. So let's see what happens if this is my transformation matrix. So what happens is this. So I start with some x and go to some x prime. That is what my transformation matrix do. So I start with some x, y, z. I go to x prime, y prime, z prime. And you will see that x prime is nothing but, so it's minus 1 here and the rest is 0, so it's minus x. Similarly, y prime is minus y and z prime is minus z. If I try to draw this pictorially, so if my x, y, z is this or this, my x prime is minus x, y prime is minus y, and z prime is minus z. Right? So this is the transformation that S is giving rise to. S is this matrix. You see, whenever I rotate anything, a right-hand system, we know that will always remain as a right-hand system, right? So what do I mean by a right-hand system? I mean that if thumb of my right hand is along x and the next finger is along y, that the next finger will be along z if I extend these three fingers, right? You can check that this has become a left-hand system. This is a right-hand system. This has become a left-hand system. And we know that by rotation, there is no way you can change your right hand to your left hand. That is impossible. Because of that, this type of thing cannot be a rotation, this type of transformation. So, it's not that all the orthogonal matrices corresponds to rotation, and it turns out that what we call spatial orthogonal matrices gives you rotation. And what are spatial orthogonal matrices? When the determinant of that matrix is equals plus 1. Okay, that plus is important. In this case, it was minus 1. That's why it was not a rotation. So that also forms a group which is called spatial orthogonal group, and this is what will represent rotation. Now this is not only the only group, this is not the only group which represents rotation. There is one more group which we learn which represents rotation, and you see that we have no distinction between these two groups in classical mechanics, and we'll see why one of these groups is more important when you try to incorporate quantum mechanics. But that's probably will be done quite later. But now let us ask the question that it's all right that we have identified a particular representation, which is that all the rotation matrices we can write in terms of the spatial matrices in the spatial orthogonal group of 3 order. But what are those matrices? What are rather the 3 parameters or 3 coordinates of my choice that can be for such orthogonal transformations. Definitely the direction cosines as being used here does not work out because they are way more in number than the required ones. Now the answer to this comes from the fact that I can now get a particular rotation by successively doing different rotations, which means you see that I can move in 3 dimensions in space. I can rotate in 3 dimensions in space. So what I can do is I can constitute rotations about 3 different axes. Okay. So what I will do is constitute rotations about 3 axes, obviously orthogonal axes. So let me write that. Okay. So 3 rotations which are orthogonal to each other. So let me, to demonstrate that, what we are going to do, let me draw this object, because then it will be easier to see what is happening. And let me attach the axes with them. So this is x, this is y, this is z. Okay. Now which way I will take these rotations is completely of my choice. So let us take a particular choice. Okay. So first is rotation about z. So if I do a rotation about z, then what happens? So I have this 3 coordinate system x, y, z. If I do a rotation about z, that's essentially means a rotation this way. So x and y will change, but the z will remain fixed. So this will become x prime, y prime, but z. So what I mean is, this brick will now look something different. Or this looks very complicated. So let me change a little bit. Okay. So this has come to there by the rotation about z. Now how do I represent the rotation? Well, a rotation about z I can write as a rotation with respect to rotation by an angle phi. Okay. So what has happened, if I look from top, what has happened is I had this coordinates x and y, which has now changed to x prime and y prime because of this rotation by angle phi. So if I have any point here, then the transformation matrix will be given as, so z doesn't change, z will remain 1, and the corresponding this will be 0 and 0, and it's just a simple rotation. So this is cos phi sin phi. Let me just write the rotation matrix, or let me write it here. So this is T. Let us give it a name. So let us call this phi, T phi. Let me also put Z here because it's a rotation about Z. So this is nothing but cos phi sin phi 0 minus sin phi. I guess that all of you know 2-dimensional rotations. That's all that we are doing here. Okay. So that is a rotation about z axis. Z remains 1. Similarly, next what I will do is, so again this is my choice and I'm going by a particular choice obviously. And okay, so this rotation is also counterclockwise. Okay, so that is how I move. So the clock moves this way, I move counterclockwise here. Rotation about x prime, and say by theta c0w. Okay. Why I say x prime? Because remember, now I am in this set of coordinates. I am here. So x has changed to x prime. So now I am doing a rotation about that x prime. So x prime, y prime, z now will go to x prime, will remain x prime, y will change, and z will also change. Okay. So in this picture will change something like this. And pardon me for my limited ability of drawing. So x prime orientation remains as it is, y prime changes, and z prime changes. This goes to a double prime, this goes to z prime. Okay, and you can write down a t phi x prime now, and so it's about x prime. So x remains as it is, and I get cos theta. Now it is about, the angle is theta. The third one, I do a rotation by angle psi counterclockwise. But now, with respect to z prime axis. Okay. So you may ask the question, why not y? You can choose that, but then it becomes a little bit more complicated. This is one choice that this is one choice you can make always. Okay. So what is this? So this is just the first thing, but now replaced by psi. Looks exactly as the first rotation matrix, but now replaced by psi. Okay. And I know the total rotation. So first I will get that phi rotation about the z axis. Then I will have to operate by, so remember that you have to go this way because here will be the vector sitting. So it will be operated by this first. And then I have theta rotation about y prime axis. And then I have psi rotation about z prime axis. I'm not drawing the rotation here again, but okay. Now this, once I write down this, now I will get a T matrix. I'm not writing down all the components. So what you should do is, homework is multiply these three matrices in this particular way. That will give you this matrix. And in this matrix, I have phi, theta, and psi. Only these three parameters. And these three parameters, if you change, you can get any rotation. So if I define the matrices this way, these matrices are called, these three angles are called Euler angles, because this is the choice that Euler made to define these three rotations. Now, in terms of these three Euler angles, I can describe any rotation, which means now these three Euler angles can be just the three generalized coordinates which describing the rotation. So at the end of the class, we are at the end of the class now, today's lecture, and we have identified three angles which can give these rotations. Now, it can be done in many different ways, obviously. So this is just only one way I described to you how you can get three angles which describes the rotation. It's obvious that you can choose to rotate in some other axis first and then proceed, etc. And there are different ways of doing it. So let me just highlight to you three different ways. One is called X convention, which is just what you have just learned. This gives you Euler angles. And this is first Z rotation, then so what did we do here? First Z and then Y, right? I think this is right, but we'll check. And then Z. Sorry. I'm sorry. So if I do it this way, first Z, then X, and then Z, so that is called Euler angles. The Y convention is first Z, then Y, then Z again. And then you have XYZ convention, which is done this way. First Z, then about Y, and then about X. This gives you also some named angles called Tate-Bryer angle. But they are just different conventions. We can stick ourselves to any one of them. Okay, what we discussed here is the Y convention. I think the X convention will give you the Euler angles. But anyway, so that we can check. Okay, so what we have done today? So we have essentially the entire discussion. We have done a few things. We have realized that the rotations can be given in terms of transformations. The transformation can be written in a 3×3 matrix form because this transformation has to satisfy certain properties. This transformation matrix has to be orthogonal. It will be a part of the special orthogonal group where the determinant of the transformation matrix is 1. And then finally we identified how any of these three different ways or many different other ways are possible, how the three angles can completely describe this transformation matrix. So what all we have to do to study the dynamics or the mechanics of this system is to see how these three angles changes with time. Okay, that's it for today.